For today's quiz, we're going to use this piece of copper wire. Now, copper wire is usually extruded or it can be pulled. Often when it's a little bit warm, they'll have a massive press. They'll have a small die or orifice or hole. And as they push this through, a cylinder of this copper is going to be coming out the other side. And again, they can pull it. Regardless, we end up with a nice piece of copper wire. And this doesn't want to bend. This is probably 10 gauge solid copper wire. Our question for today is simply, let's say that I could uniformly stretch this to twice its length. If I was incredibly strong. What would happen to the wire's resistance? Our question looks something like this. I'll hold this up now. As always, mark your answer as completely as possible. Enlist your confidence. Okay, typical student responses are usually three. The first one is really good intuition. Students will say, I think this is a trick. I've got the same amount of copper here. All you're doing is stretching it and changing the shape. That's really good thinking. But then we'll ask, okay, but what about the resistance? They'll say, same amount of wire on the original or the stretch piece, the resistance would be the same. Others will say, look, if you stretch this, you're going to end up making it thinner. A lot of students have used straws, things of that nature, and they're saying, if electricity flows, I know if I have a straw and it gets thinner, it's going to be harder to get things through. So they would say the resistance would go up. Others would say, yeah, I buy that explanation, but if I ended up having a thinner straw, whatever's flowing through there would probably try to go faster, and maybe that would reduce the resistance. Most of the other students are not going to buy into that one. But those are our three typical student responses. All right, let's see if we can provide an explanation for this. Let's build on that student intuition where they know that this wire, and I have them drawn, not to scale, but this is our original piece of wire. They know that the volume is going to be the same. Look, I have the same wire here. I'm going to have the same wire when I stretch it. So when I drew this one, I took whatever length that was and simply made this one twice as long. I measured it out. So we'll call that L. We know that the volumes are the same. Now look, students have intuition, but often they don't have the tools to kind of put everything together. So that's one of the things that we want to do is try to show them how we can mathematize things, and it's a wonderful tool to allow them to express themselves. So we might push them and say, what is it that you actually know? And they'll say, look, they're the same wire. We might say, well, what does that really mean? They'll say, it's the volume. And we can do something like this. We can say, look, the volume over here, we could say, that volume must equal that volume. But look, if we say V equals V, we're really talking about the situation of a wire before it was stretched and after. So we use this little kind of a counting tool. We like to put a little apostrophe right here. And that apostrophe means the thing that happened after. And that allows us to, compare that side to this side. All right, now that we've got that, students need to figure out, well, what is volume? Volume, of course, has something to do with length. If this was rectangular, most of them would say length times width times height would give volume. But because we chose to use a round object, we can end up saying, well, this has got some area A. So I'll put area right here. And they know that area times length would give volume. And they can just do that with the dimensions. They could say, well, if that's like meters squared, another meter for length, meters cubed. So I can put a where statement, which is another really good tool. Have students start to write what they're thinking. We could put where we could say volume equals our area times our length. Now, if that's the case, we can end up putting this volume is equal to an area times a length. This side would also be area and length. But remember, they're different than that area and length because we've changed the shape. So I could say area after times the length after. Again, using those little apostrophes showing that we're talking about the after picture here. Now, we already know that this is length L. And getting students to draw pictures out, really helpful. We'll say, oh, we actually know something about this L over here. It's twice the length of this. So I can call this one our L after, and that's going to be equal to twice our original L. And we might even put that as a statement right here. We might say, where L after equals twice our original length. Now, once we put that in there, we have to figure out what happened to the area. I think most students right away are going to know, look, it gets thinner. It's going to have a smaller area. But I'll put a little A right here and an apostrophe. But then you push your students to keep going with their mathematics. They could say A times L must equal our A after. Now, we know that instead of this L, I can put 2 of our original L in here. So I'll put 2L like that. They'll say, wait, now I've got an L on both sides, and we can cross that out. So you could say, sure, cross that one out, cross that one out, and now we can solve for what our A after is. And our A after, if we divide by 2, would simply be our original A divided by 2. So we now know that area is going to be half the area of the original. So that's a pretty good statement right there. That's a fact that we just have essentially proved. So that A would be equal to our original A divided by 2, or we could write that as 1/2 our original A. Now that we've got that, maybe we should partition this off, because we now have figured out our volume, which is wonderful thinking. But a lot of students will get stuck here, so we'll have to go a little bit further. Let me just draw this out so that we know that we're no longer working on that part of it. Most of our students can figure out about resistance. They'll say, look, if we think of flow, our resistance will increase if it gets longer. It's going to be harder to get through a longer tunnel, but if the tunnel is bigger and I can get more people through there or cars through there, whatever the tunnel's trying to control the flow of, most of them will say area is going to be, well, we should say resistance. We could say the resistance of this, and I'll just put R, I'm going to use this resistivity. That's just what the material is made of. It's going to be copper here. It's going to be copper on the other side. Sometimes they'll include this. Other times they won't. It's all going to work out. We certainly know that if I increase the length, I'm going to end up having more resistance. And if I had more area, the area got bigger, it'd be less resistance. So most students can get this. And most of them are going to now see right away, oh, that one has more resistance. And this is where you want to push them. You want to say, great, but how much more resistance? We'll use some of the ideas that we started up here, and we could say, well, let's rewrite that formula for the after picture. We're not saying they're equal now. Up here we are doing, equation, we're equating them. This one we're not. We're going to write this separately, and we'll say, well, the resistance after would be whatever that resistivity is after, times our length after, divided by our A after. Now, right away, you can help them and say, look, we're not changing the resistivity, so let's cross that one out. Cross that out, cross that out. They're the same. So the wire hasn't changed, but we did change the length, and we did change the area. So now that we have it right here, I would pause and give your students a few moments to see if they can come up with a numerical value of what that resistance is going to be. Okay, we're going to help our students through this a little bit. They need the confidence to be able to work with numbers, and we'll give them a new tool here. Instead of using equations, there's something that we can do. We can set things to their proportions, or make a proportionality statement. And we'll use that on this first case. We'll say, we can end up saying, look, our resistance here is proportional to our length all over our area. Then we're going to introduce this other idea that we can say, look, let's just choose the easiest possible numbers. We'll normalize our first case by setting our length and our area equal to 1, because 1 over 1 would give us a resistance of 1. We're not saying that we know the exact resistance is equal to 1, but we're going to compare it afterwards, and we'll be able to say, if this was 1, what would this be? So I'll just put this in parentheses above. I'll say, we're going to say our length here is 1, and our area is 1, and 1 over 1 would give us an overall resistance of 1. We can now do the same thing on the other side. Again, remember, the resistivity, we just are ignoring that because it's the same piece of copper. The value would be the same for both sides. Area and length are going to be different though. So let's start working over here. Make this a proportionality. We could say, well, this resistance is also proportional to our L after all over our A after. Now we know that each of these, the L is going to end up being twice our original L, and our area is going to end up being half of our original. So I can put that right here. I'll put this as 2, and then I'll put 1/2 here like that. So really what we're asking is, what is 2 divided by 1/2? Now that might seem easy, but most of our students are going to struggle with that. Maybe I'll push this off to the side here. So we're really asking, what is 2 divided by 1/2? And that'll give us whatever this resistance is going to end up being. So I can end up saying, well, 2 can be written another way. I can write 2 as 2 all over 1. It doesn't change anything. When you divide by 1, you still get the thing. So I'm going to rewrite this 2 on top as, I'm going to write 2 all over 1 all over 1 all over 2. Now, there's another thing that we can do, because this is exactly equal to that. But I can rewrite another thing by multiplying by the number 1. Whatever number I have, whatever thing I have, when I multiply it by 1, I don't change anything. So I can multiply anything by 1. So I'm going to take this 2 over 1 over 2 and multiply the entire thing by 1. But another trick that we can do is we can put anything over itself still equals 1. I could take 5 over 5 still equals 1. In this case, I want to get rid of this bottom part of the fraction. So what I'll end up doing is I'll choose a number that will do that. I'll multiply 2 over 1, 2 all over 1. I hope everyone can see that this big fraction, 2 over 1 over 2 over 1, is just 1. And I'm multiplying it by my original numbers, but I'm doing it in a way that is going to force this 2 to cross out with that 2, that 1 to cross out with that 1. We're going to end up with 4 all over 1, which equals 4. So in other words, when I ended up putting my 2 for my length and my 1/2 for the area, that's really going to tell us that our resistance is going to end up being 4. So if our original wire had a resistance of 1, or whatever it is, this will end up being 4 times that. Interesting tools to help our students think through, gives them a language, gives them a way to express themselves, using numbers for their intuition. All right, that's your quiz for today.